Welcome to UBG Bytes. We're doing a deep dive today into macOS initial access vulnerabilities. Really crucial stuff for all of you working in information security. We've got some, pretty interesting material to get through, and we really want to try and answer a couple of key questions. First, does an attacker always need to trick a user, classic social engineering, to get that first foothold on a Mac? And second, Apple's got all these security measures, code signing. How are attackers actually getting around that? Okay, let's jump in.
Yeah, it's interesting right off the bat because no, gaining initial access doesn't always need user interaction. A really good example here is CVE 2025-31191. To really get it, though, we kind of need to talk about the macOS app sandbox first. You can think of it like a restricted play area for apps. It limits what they can access, network, file system, that kind of thing. And if you get an app from the Mac App Store, these rules, the sandbox rules, they're mandatory. Apple insists.
Right, it's about walling things off, creating a safe zone. But then you mentioned security scope bookmarks. How do they fit in?
Okay, so those are meant to give sandboxed apps a way, a controlled way, mind you, to access specific files or folders outside their sandbox. Think of it like a temporary pass, a key card. And that card should only be given out if the user explicitly says, okay.
Okay, so user consent is the key.
Ideally, yes. When a user, deliberately gives an app access, maybe through something like the Grant Access to Multiple Files API, that permission gets saved using these bookmarks persistently. And there's this critical piece, a system process called Scoped Bookmark Agent. It's not sandboxed, and its job is to check these bookmarks are legit and then issue temporary access tokens, sandbox extension tokens they're called. These tokens basically stretch the app sandbox just enough to allow that specific access.
Okay, so how does Scoped Bookmark Agent know a bookmark is real and hasn't been, faked?
Good question. It relies on crypto. Signing. There's a key. And it's derived using the app's unique ID, its bundle identifier, plus a secret key. And that secret is stored securely, or it's supposed to be, in the macOS keychain. Specifically in an entry called com.apple.scopedookmarksagent.xpc. The whole idea is that only Scoped Agent should be able to read that secret. Seems solid, right?
Seems solid, yeah. But I sense a but coming.
You sense correctly. The vulnerability, CVE 2025-31191, it targets a weakness in how the permissions, the access control list, or ACL, for that specific keychain entry are handled. So a malicious app inside the sandbox, it can't just read the secret, but it can delete the original entry.
Delete it, okay.
And then it creates a new entry, same name, com.apple.scopedookmarksagent.xpc, but this time containing a secret the attacker already knows. And here's the kicker. When creating that new entry, the attacker also gets to set its permissions, its ACL. They can grant read access to Scoped Bookmark Agent.
Whoa. So they swap out Apple's secret for their own and then tell the system it's okay for the agent to read their fake secret. That's sneaky.
It really is. So the exploit path looks like this. Delete the real secret, add the attacker's known secret. Then the attacker can calculate the signing key because they know the secret and the app's bundle ID. After that, they just create and sign their own malicious bookmark entries in the secure bookmarks.plist file. Now, the sandboxed app can write to that file. It's in its own container.
Right.
So when the app calls grant access to multiple files again, Scoped Bookmark Agent fetches the secret, which is now the attacker's secret, validates the fake bookmarks, and happily grants the access tokens. Boom, sandbox escape. And absolutely zero user interaction needed.
Wow.
Yeah, it was a pretty significant issue, affected any sandboxed app using these bookmarks. It's important to say Apple did patch this March 31st, 2025. So keep those systems updated, folks.
Definitely. That just completely flips the script on needing user interaction, doesn't it? The whole point of that API, grant access to multiple files, is the user explicitly picking files.
Exactly. This vulnerability just bypassed that completely.
But, okay, the more, let's say, traditional social engineering methods, there's still a big deal, right? Tricking users.
Oh, absolutely. While that CVE was, a technical exploit, manipulating users is still incredibly common. Think about getting someone to install a malicious launch agent or maybe a dodgy configuration profile. These are really common ways attackers get persistence on macOS.
Right. Persistence meaning the malware sticks around.
Exactly. Sticks around after a reboot.
Right.
So trick a user into installing a bad config profile, and suddenly the attacker can mess with browser settings, maybe route traffic through their own DNS servers, set up VPNs without permission.
Nasty stuff. And launch agents.
Very common. They often get dropped into the user's library folder, and they just run automatically every time the user logs in. It's a classic persistence technique.
Okay, so we've got this really clever no user interaction needed vulnerability example. Now let's talk about bypassing code signing. Apple puts a lot of effort into this, making sure only trusted code runs. How are attackers defeating that?
Well, there isn't just one way, as you might expect. Several different approaches. One key method, actually kind of related to what we just discussed with the CVE, is finding and exploiting vulnerabilities within processes that are already signed and trusted by Apple. In the bookmark case, the flaw wasn't in the app itself, maybe, but in the system's mechanism for handling those bookmarks, which involves signed Apple code. So, by manipulating the keychain and bookmarks, they got code execution despite the signing.
Ah, I see. So it's not necessarily breaking the signature itself, but finding a weak link in a signed chain.
Precisely. You're leveraging a trusted component against itself. Another big area is process injection. Now, the old school methods, using things like task forfeit or the mock-vim APIs to just reach into another process's memory, Apple's really cracked down on those. You generally need root access now. And they just flat out don't work against apps using the hardened runtime or apps signed by Apple itself.
Makes sense. You wouldn't want just any app messing with system memory. But I bet attackers found other ways.
They did. There was, for instance, a vulnerability, now patched, CVE 2021-30873. It used a flaw in how AppKit, the UI framework, saved its state. This actually allowed code injection into other AppKit applications. It was pretty powerful use for sandbox escapes, even bypassing SIP, System Integrity Protection.
SAP bypass. Wow.
Yeah, but like I said, Apple fixed that one in macOS Monterey.
Okay, so that door's shut. What else is in the attacker's toolkit for injection?
Another really interesting angle is abusing debugging interfaces from third-party frameworks like .NET Core. Its debugger creates a session, right, for finding bugs.
Yeah.
But it also exposes these low-level functions, things like mthread memory and mtwrite memory. These let you read and write directly to the memory of a running .NET Core process, kind of outside the normal macOS rules.
Using a legit debug tool as a way in.
Coder.
It is. And you can use this to get code running. First, you'd inject your malicious code, your shell code, into a memory area that's marked read, write, and execute RWX.
Then you find the dynamic function table, the DFT, inside a .NET library like libcorksler.dll. It's basically a list of where functions live in memory. You overwrite a pointer in that table to point to your shell code instead. So when the program tries to call the original function, bam, it runs your code.
Redirecting traffic, essentially.
Pretty much. And there are other ways, too, like using functions like nscreate object file image from memory to load unsigned bundles, like little plugins, directly into signed processes. Again, unsigned code running in a trusted context.
Man, it feels like they're always finding these little cracks. What about software updates? They often run with higher privilege.
That's another vector, yeah. If an attacker manages to get enough privilege escalation first, they might be able to just swap out the legitimate program file that a launch daemon a system service is supposed to run. So the system thinks it's starting a legit service, but it's actually running the attacker's code. This could even happen with updates from legitimate vendors if they're not careful about protecting their update files.
And then there's just hiding the code, right? Making it hard to find or figure out, even if it's not technically bypassing signing itself.
Exactly. Obfuscation. It doesn't break the signing check, but it makes life much harder for defenders and analysts. If they can't easily see what the code does, it might run for longer before getting caught. We see all sorts of tricks on macOS, hiding scripts inside disk images, using tools like the SHC compiler to make shell scripts unreadable. Sometimes obfuscated Python scripts, though maybe less common now, really heavily scrambled Mach-O binaries, that's the main macOS executable format.
Scrabbled how?
Just making it incredibly difficult to reverse engineer. We saw this with malware like OS X Zuru, Pamafka 2. There's even a specific indicator sometimes, an MD5 hash related to the string section, C5L05ISDF400, BUZ07s, 806, AB4560A. If you see that, you know you're dealing with heavy obfuscation. Also things like run-only Apple scripts, sometimes hidden inside other scripts using hex encoding, just layers upon layers.
It's like a digital nesting doll of malware. And what about newer languages like Go? I hear that causes problems too.
You're right. Go-based malware, things like Poseidon, Sliver, they often bundle their entire runtime environment with the malware. So analysts have this huge chunk of legitimate Go code they have to wade through to find the small malicious part. It just makes analysis harder, slower. And we've actually seen Sliver, for instance, disguised as a signed Apple software update binary using launch agents to persist.
Wow. Okay, one last area. Developers themselves, can they be a weak link?
Definitely. We saw this with malware called XeSet. It spread through infected Xcode projects, so developers share code, maybe download a project from somewhere, and boom, their whole development environment is compromised. The malware runs right there, potentially stealing credentials or injecting code into the apps they're building.
That's scary, compromising the source.
It is. It hits developers right where they work.
Okay, so let's try and pull this together. It seems pretty clear that, one, getting initial access on macOS doesn't always need user interaction. That bookmark vulnerability is a stark example of a purely technical bypass. And two, bypassing code signing isn't just about cracking signatures. It's this whole collection of techniques exploiting flaws in already signed code, finding clever ways to inject code into processes, messing with updates, just hiding really well through obfuscation.
Yeah, and leveraging things like third-party frameworks or even the development process itself.
It's way more complex than maybe some people assume,
Yeah.
a constantly shifting landscape.
Absolutely. The main thing to remember is that macOS security has layers, yes, but attackers are always poking at those layers, looking for ways through, around, or under them. Understanding these initial access routes and these signing bypasses is just, well, it's essential if you're trying to defend macOS systems effectively. You need to know what you're up against.
Couldn't agree more. This has been another Byte by UBG.